So we're starting a new topic today. And in some sense, a lot of what we talk about this week is going to feel really familiar. Because we said, hey, think back to one of the first few things we talked about, way back, maybe first week, second week. We talked about differential equations, like x prime equals ax. We're like, oh, these are great. We know how to handle those. And in fact, we could say, look, if you give us that differential equation and you gave us an initial condition, we could tell you the solution really easily. We didn't even have to think. X of t was e to the at times x of 0. Wow, wonderful. But where are we now? Well, now, slightly different. X prime equals ax, but capital A. A matrix, and we have initial conditions, not a number, a vector, but maybe, we can still say our answer is e to the at x of 0. So our goal for today is basically to say, what is this? Does that even make sense? And how do we find it? So that's where we're going for today. That's one of our two topics this week. All right, so my microphone is making lots of noise. Hopefully it's not the beer. I haven't saved up enough. Usually I can only afford one haircut a year. The life of a mathematician, Those engineers, they can afford at least 2 or 3. All right. I hope that's better. Okay, so where are we going to start? Well, let's suppose we start with x prime equals ax. We know how to solve it. We talked about, okay, you find eigenvalues, you find eigenvectors, you combine eigenvalues and eigenvectors. Maybe there's a bump, maybe there's not, maybe there's complex. That's okay, we can handle it. And we can find solutions. So we start by saying, well, let's just make a matrix with those solutions. So the fundamental matrix, capital phi of t. The first column, solution 1. Second column, solution 2, so forth and so on. Now there's a couple of things. First off, there's this word A, fundamental matrix. Why do you think we use the word A and not the? Yeah, there could be more than one. Some things that you could do, you could change the order of the solutions. You still have a full set of solutions. You could even do things like linear combinations of solutions. So it's not like there's one fundamental matrix, there's many. Of course, there's a preferred one, that one. But we're getting to that story. All right, so that's why we use the word A. Now another comment, which is mentioned here, we've actually seen this matrix before. We've walked past it, didn't spend a lot of time getting to know it very well. It's the Wronskian. So if you remember, the way you compute Wronskian, when you have these systems, is each column was a solution. So say, oh, it's nice to see you again, Wronskian. And you might say, well, what did we care about the Wronskian? Well, we cared whether the Wronskian was 0 or non-zero. So it turns out when the Wronskian is non-zero, that's another way of saying you can find the inverse of the matrix. And that's important if you're looking for a particular solution. Now, there's an observation, and this is just to sort of say, we've talked about matrix multiplication, but there's another sort of perspective you can have for matrix multiplication when you have a matrix times a vector. Now, normally, if we did this computation here, well, we would say, for example, we'd say the first row, first column. We just work across the first row, work down the column. So it'd be A11, B1, A12, B2, and A13, B3. And then, of course, the other two were the same. But it turns out that there's another way to think about when you multiply a matrix by a vector, it's really saying, oh, it's a combination of the columns of your matrix. So my claim is that this is B1 times the first column, B2 times the second, and, oops, that's not my claim. That should be a 3. Okay, that's what happens when you do cut and paste. And B3 times the third column. Now, how can we check? Well, we just carry it out. What would the top entry be? A11, B1, right? And then you add A12, B2, and you add A13, B3. And the other ones are the same. In other words, they match. So why is this helpful? Why is this perspective helpful in understanding why we care about the fundamental matrix? Well, recall we have this cool idea, this really super idea, really, when you think about it, superposition. And that says, look, every solution that we care about looks like C1, X1, C2, X2, ... plus Cn, Xn. Well, now if we combine this notion of like, oh, if I want to just take a linear combination of the columns, it's just the same as multiplying by a vector. And then I say, oh, look at where my columns are. My columns of phi are these vectors here. This becomes phi. And now I realize as I'm saying this out loud, is it really phi or is it phi? Phi, phi, pho, phum. I don't know. But the point is, it's phi of t, and then what's this vector that goes here? What's the vector? It's the vector of the coefficients. And so now we can say, look, every solution has this form. So essentially, initial value problems come down to saying, solve for this vector. What's the right vector to pick here? So, all right. So we'd like to know, is there an easy way to solve for this vector? Because if there is, life is good. And if there's not, well, it wasn't any worse than before. So, all right. So, well, turns out there is a nice way. Here's a fact. If x prime equals ax, and you have initial condition x of 0, then x of t is phi of t, phi of 0 inverse x of 0. Wow, that's amazing. Okay, good. So given what we just talked about, the real claim here is saying that this piece, this is what we were calling in the previous slide, C1, C2 up to Cn. In other words, phi of 0 inverse x0 gives us just the right combination of coefficients. Okay, so there's an exercise. Verify the above fact. Well, what do we need to verify? The claim is that we have x prime equals ax and initial condition x is 0, then this is the solution. What things we need to verify? Well, initially I might feel inclined to give a hint, but initial conditions. Yes, someone said, hey, we have to verify initial conditions. Okay, that's true. How could we verify initial conditions? How do you verify initial conditions? You plug in. Okay, so we'll check our initial conditions. All right. And, well, we say x of 0 here. Does this equal, that's our question, phi of 0, phi 0 inverse x of 0? Well, do you notice anything about that expression? So that's phi of 0, remember that's a matrix. Wait, it's what? 1. Or what's the equivalent of 1 for a matrix? It's the identity matrix. If I take the identity matrix times x is 0, we get x is 0. So that's the verification. It satisfies the initial condition. When you plug in 0, you get the right numbers. Okay, but that's not the only thing we have to check. That's not the only thing that has to be satisfied. We now know that it has the right initial values, but what else do we need to make sure it satisfies? Well, we have to verify that it satisfies this differential equation. All right, we now know when we plug in 0, we get the right numbers. How do we know that x prime equals ax? Okay, so let's think about this. So notice, what is x of t? Well, coming back here, we say, look, that's really phi of t. And now I don't know why I'm doing this, but half the time I write phi, I put these bars on, and half the time I don't. I'll try to be consistent. It's phi of t times some vector, c1, c2 to cn. But remember, we know what phi looks like. It's x1, xn, and then we have our c1, c2, cn, which means it's c1, x1, plus c2, x2, plus cn, xn. That's what we know x of t looks like. It looks like a combination of each of these. On the other hand, what are some things we know about these xi's? So we have that each xi is a blank to x prime equals ax. It's a solution. Each one is a solution. So they're a combination, and in other words, their superposition, that's what we mean by their combination, is also what goes there? Is also again a solution. Since we know that the pieces that are being used to make up this expression are indeed individual solutions, then putting them all together gives a solution. And so we're done. Now, what does this all mean? Well, remember, we started by saying, hey, it'd be nice if given x prime equals ax with x of 0 given, we wanted to say that x should look like e to the at x of 0. We've now shown that x is equal to phi of t, phi 0 inverse x of 0. So essentially, one of our takeaways for today is that e to the at is this phi of t, phi of 0 inverse. Now that's not the only way to go about computing it, but that's one of the ways that we'll think about it to begin. All right. Well, we should do an example. So, given x prime equals 4, 2, 3, minus 1x, find phi of t, phi of 0 inverse. And then there's a question, does this answer depend on the order we put x1, x2 into the columns? And does the answer depend on how we scale either of x1, x2? Actually, let's go ahead and answer this question first. So, remember, we talked about how phi of t is a matrix, right? Because we said, oh, we could do things like rearrange the columns, scale columns, combine columns. So phi of t as a fundamental matrix is not unique. The question is phi of t, phi of 0 inverse unique? In other words, does it depend on how we fill in the phi of t? What do you think? I have to be careful because of the way I asked my two questions. So does the answer depend on how we fill in phi, or does it not depend on how we fill in phi? Well, remember, we know that x prime is equal to phi of t, phi of 0, inverse x. Okay. So this is the part we're asking, can this vary? Whoops, I forgot to put an x0 there. Can this vary? So that's my first question. Can this vary? And my second question is, why not? Okay, anybody have an answer for the first question? Can this vary? No, it cannot. It always has to be the same. It can never change. Never. No matter how you choose to put in the columns. No matter how you scale your columns. So that you can actually take inverses, of course. Why not?
Otherwise, that would no longer be true.
What would no longer be true? There's a word that's... I'm almost tempted to do what we did a year ago. Should we play some hangman? All right. It's... There's a word about differential equations, and in particular in solutions to differential equations. That shouldn't be an x prime, that should just be an x. Well, okay, so remember how the game works. You don't guess words. You start by guessing letters. I. Okay, I is a good one. E. E is another good one. All right. E. There we go. A. Oh, no, A. Oh, yeah. Oh, sorry. I'm sorry. Sorry about that. S. N? Q is a bold move. Uniqueness. So, there is a unique solution. If this varied, then I could still have the same initial conditions. I'd have different solutions coming out. Because I can only have one solution, solutions are unique, that says this can't vary. It always has to be the same at the end of the process. All right, so that's why that won't vary. So the answer is, does the answer depend? And the answer to that phrasing is no. Okay, so back to the first part. Let's find this. So we start. If I want to find phi of t, what should I be finding? I should be finding the solutions, so then we can figure out what fills the columns. Okay, so if I want to find the solutions to this kind of differential equation, a system, where do we begin? Eigenvalues. All right. So we're going to get really good at this, I hope. All right, we're taking our 2 by 2 determinant A minus lambda I. So that's 4 minus lambda minus 1 minus lambda. Subtract 2 times 3, so that diagonal going down, subtract diagonal going up. All right, we'd have minus 4 lambda plus lambda squared minus 6. That's lambda squared minus 3 lambda minus 10. Does this factor nicely? How does it factor? Minus 5 and plus 2. Lambda minus 5, lambda plus 2. We can, of course, check lambda squared plus 2 lambda minus 5 lambda is indeed minus 3 lambda. And 2 times minus 5 is minus 10. All right, good. All promising stuff here. So, we set this equal to 0. What are our eigenvalues? 5, negative 2. All right, what comes next? Eigenvectors. All right, so let's start with 5. So I'm going to take a minus 5I. So that would be minus 1, 2, 3, minus 6. And we're trying to find some vector, not 0, such that minus 1, minus 2, 3, minus 6 times this new vector gives us 0, 0. Do we see a vector that works? 2, 1 works. You can, of course, check it. So that says an eigenvector for 5 is 2, 1. All right. Now, we'll do a similar thing for negative 2. So we'll go to our a minus lambda I, but we're putting in lambda equals minus 2. So it becomes minus lambda becomes plus 2. So 6, 2, 3, 1. We're looking for some vector that once we multiply 6, 2, 3, 1, we get the 0 vector out. Well, do we see such a vector? Sorry, what? 1, negative 3. Does that work? No, 6 minus 6, 3 minus 3. Works brilliant. 1, negative 3. Okay, so we have our eigenvalues and our eigenvectors, which means we have our two solutions. E to the 5t, 2, 1, and e to the minus 2t, 1 minus 3. So those are our two solutions. Now, we're ready to write down what is phi of t. Doesn't matter which order we put it in, so we'll just start here. The first column will be our solution with eigenvalue 5. So that's 2e to the 5t, e to the 5t. Our second, e to the minus 2t, minus 3e to the minus 2t. All right. Are we done?
No.
No. What do we need to do next? Yeah, we need to do phi of 0 inverse. So let's first off, what happens when you plug in 0? What do you get? 2, 1, 1, negative 3. In other words, it's your eigenvectors. Not a coincidence. Inverse. All right. Do we remember how to take the inverse of a 2 by 2 matrix? 1 over. What's the determinant? 80 minus BC in our case. So minus 6, subtract 1 gives minus 7. And then swap the diagonals. And then what happens to the off diagonals? Change the signs. Okay, so we're ready to write down our last computation. So it's phi comes first. Phi 0 inverse comes second. So it's 2e to the 5t, e to the minus 2t, e to the 5t, minus 3e to the minus 2t, times negative 1/7, 3, negative 1, negative 1, 2. Now the negative 1/7, you can go ahead and put that in the front, because a constant can just be pulled through the computation. All right, so we just carry this out. Minus 6 e to the 5t, subtract e to the minus 2t. Then the next one, minus 2 e to the 5t plus 2 e to the minus 2t. And coming down, minus 3 e to the 5t plus 3 e to the minus 2t, and minus e to the 5t plus 6. Is that right? No, sorry, minus 6. Because there's a minus 3 there. Minus 6 e to the minus 2t. And we've got it. All right, any questions about that? You see the procedure. Yes? Good, so you can do it now. So, another example. Given x prime equals 5 minus 4, 3 minus 2x, find 5t, 5, inverse. Use this to find a solution. Well, the solution with an initial condition x of 0 equals 7 minus 5. All right. Do we have partial answers? Do we know what the eigenvalues are? What are they? 1 and 2. Okay. Good. Do we know what the eigenvectors are? So what's the eigenvector for 1? 1, 1. And for 2? 4, 3. All right, so we've got our eigenvalues, we've got our eigenvectors. Now, we take and we write down our solution. So we have x1. I chose the 4, 2 first, doesn't really matter. E to the 2, 2, 4, 3, e to the t, 1, 1. What comes next? 5t. And we just have these to fill up our columns. Then we take phi 0 inverse. So that's 4, 3, 1, 1 inverse. And of course, the determinant of 4, 3, 1, 1, they were nice. It's 1. So there's our inverse. And then what happens? You multiply. Now, that's because it asked us to find it. Now, I will say, well, I'll make a comment in a second here. That there's a space for a comment. And the last thing, how do we use this to find the solution? We multiply. So 5t, phi 0 inverse x of 0. So we take the matrix we just found, multiply by 7 minus 5, and this is the resulting matrix. So our solution is 48 e to the 2t, subtract 41 e to the t, 36 e to the 2t, subtract 41 e to the t. All right, now I just want to say, in practice, you probably would change the order you do some things here. And here is the order that's probably more convenient. So if you were to follow what's written here, you'll see that we said, hey, x equals phi of t, phi 0 inverse x 0. And we did it in this order. We first multiplied phi of t, phi 0 inverse, and then we multiplied by x of 0. That's certainly a legal way to do it. However, in practice, it's usually easier to do that first. Multiply the phi 0 inverse times x of 0. Now, why would this computation be easier? Yeah, numbers, exactly. Exactly right. It's just numbers involved when you do this computation and not functions. So if you wait till the last second to do the multiplication with the part with the functions, less likely to make mistakes, it's easier to carry the computations through. I see a question.
Could you get a different answer if you put x1 and x2 in, like, differently?
I don't know. Could you get a different answer? Why not? Uniqueness. So that goes back to our discussion earlier. It turns out that if you change the order, let's see, how much time do we have? Time? What time do you think you have? If you change the order, it will correct itself. So essentially, the phi 0 inverse undoes the changing the order, is what happens. And you can try it out at home, you know. Just grab these solutions, change the order. So I'm guessing probably somebody did change the order from the way I wrote it down here. Did you get the same phi 0 inverse?
Slide it up so I can see it.
Slide it up so you can see it. Did it look the same? Yes, I'm getting some yeses. Okay, so we have some tentative, it's the same. Don't just take my word for it. All right. Okay, well, good. Any other questions about this process? You will get to do this definitely like on a quiz, probably on an exam, so you want to make sure you're comfortable with this. And even if you're not comfortable, you want to make sure you can do it. All right. Well, that brings us to saying, okay, let's go back to talking about this e to the at. And we think about things that we can do with matrices. And we say, well, there's not that much. We can do things like scale and multiply and add, a few other things. And then we say, well, wait a second. Scaling, multiplying, adding, that sounds like polynomials. Like, yes, exactly. We can do polynomial stuff with matrices. And then you're like, wait a second, I took Calc 2. Everything's a polynomial. That's what you learn in the end of Calc 2, right? Your favorite topic, Taylor polynomials and Taylor series. Everything's like a polynomial, including e to the z. Which is to say, e to the z is 1 plus z plus 1 over 2 factorial z squared, 1 over 3 factorial z cubed, and dot, dot, dot. So you can write e to the z as this big polynomial. And then people say, well, great. Let's just plug a in where we see z. And so you have, well, we'll come back to that. A, 1 over 2 factorial a squared, 1 over 3 factorial a cubed, so forth and so on. So it's 1 over k factorial a to the k. And they might say, well, wait a second. How did 1 become I? Well, one reason is so it made sense. But another reason is you could say, really, this 1 represents something. It represents z to the 0. If I take a matrix and raise it to the 0 power, what do I have? You have the identity matrix. So that's why you have the I there. And so we're like, aha, here's how we're going to talk about computing a polynomial, a matrix, e to a matrix, e to the a. So let's do it. Let's do a really easy case. So if I have my polynomial a, 0, 0, b, so this is what we call a diagonal matrix. And the reason we call it a diagonal matrix is it only has things that are non-zero are on the diagonal. Compute e to the lambda. All right, well, let's make a couple of notes. We know what lambda looks like. What about lambda? Well, oh, yeah, that was right. I'm not really good with my capital Greek letters sometimes. I was like, wait, is that right? No, it's right. So this is not like a mistyped a. This is capital lambda. And the reason we use capital lambda is we usually use lowercase lambda for the eigenvalues, so somehow capital lambda is like all the eigenvalues thrown together. All right, so if I take a times 0, 0b, and multiply a, 0, 0b, what does that look like? So carry off. First entry, next entry, next entry, next entry, b squared. Oh, that's very convenient. How about lambda cubed, which is really like lambda squared times lambda. Well, we just computed lambda squared. Now we're going to multiply that by a 0, 0, b. What's the result? A cubed, 0, 0, b cubed. What if I took lambda to the power k? A to the k, 0, 0, b to the k. All right. Well, cool. In other words, it's easy to figure out our individual pieces. So we can say e to the lambda, well, that looks like 1, 0, 0, 1 plus a 0, 0, b plus 1 over 2 factorial a squared, 0, 0, b squared, 1 over 3 factorial a cubed, 0, 0, b cubed, and so forth and so on. Well, now let's just add these matrices together. In the upper left corner, you get 1 plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed, and so forth and so on. Upper right corner will be 0, because they're all zeros. Bottom left, 0. Bottom right, well, 1, b, 1 over 2 factorial b squared, 1 over 3 factorial b cubed. And now we're like, wow, okay, so that's interesting. Now, have we seen anything at all that looks like 1 plus a plus 1 over 2 factorial a squared plus 1 over 3 factorial a cubed? Anything at all? Oh, it's here. It's e to the a. Wow, that's cool. And down here, that's e to the b. Nice. Okay, so for diagonal, easy. But you might be saying, but Steve, most matrices aren't diagonal. Like, come on, don't rain on my parade. But here's the good news. Most matrices aren't diagonal. This is a true statement. You speak the true truth. But they're almost diagonal. Okay. So, here's a fact. Now, in the interest of time, just remember you can download this. You don't have to write it all. And this is the part I want you to focus on. It says, hey, if you have a nice set of eigenvectors and eigenvalues, so lambda 1 through lambda n are your eigenvalues, v1 through vn are your eigenvectors, you make a matrix with your eigenvectors, you call that B. Then your original matrix A looks like B. These are your eigenvectors. A diagonal matrix with your eigenvalues, B inverse. That's true. Now you might be saying, well, why is that true? Well, what you can do is you can compare A times B versus B times what we'll call capital lambda. And if you just go through column by column, which is what this EK is doing, you compute what's happening. Now, what is EK? EK is just looks like this. It's a little vector, which is a 1 in the kth position, and then it's 0 everywhere else. So it's just, EK is just a way of saying grab the kth column, and you go through and say column by column they match. So AB equals B lambda, and then you multiply by B inverse. Well, how does this help us in computing e to the a? Well, if I have B lambda B inverse times B lambda B inverse times B lambda B inverse, so forth and so on, what do you notice about these little pieces here? B inverse times B does what? it cancels out. It's like the identity. So they all sort of just bloop, disappear. So it's like I have b and a bunch of lambdas b inverse. In particular, it's b lambda to the k b inverse. So it's like, wow. So a to the k, it's actually pretty simple. Once I have in the right form, you're just raising these eigenvalues to the kth power. Now, you apply this, you say, all right, what if I want e to the at? Well, you run the computation, and it turns out you have your eigenvectors of a, the inverse of that, and in between, it's e to the lambda 1t, e to the lambda 2t, down to e to the lambda nt. All right, well, let's see. We have 2 minutes. You think we can do this? Yes, I think we can. Find e to the at for a equals 4, 3, 2, minus 1. Now, I know there are pessimists here in our crowd who think we can't finish this, but they forgot we did the work. It's this same matrix we talked about earlier. Okay, so our eigenvalues and eigenvectors. We copy. See how much faster it is when you copy? Now, by the way, you're not supposed to do that during an exam. But just full disclosure. All right, so here we go. Those are our eigenvalues and our eigenvectors. So our matrix B looks like 2, 1, 1, minus 3. Those are my eigenvalues. My matrix lambda looks like 5, 0, 0, minus 2. B inverse. Now you're like, aha, Steve, we didn't do that. Except we did. It's right there. That's the inverse. And now you're like, whoa, Steve, this is like, it was meant to be. It was meant to be. This is just to illustrate that something is going on that's really cool. So we're going to tie the themes all together here. Okay, so we have our b, we have our lambda, we have our b inverse. And therefore, we come back and say, remember the previous slide. E to the at is b diagonal b inverse. So if we follow the formula, e to the at is b e to the 5t e to the minus 2t, 0, 0. So this is the part where you have to remember, I'm taking e to the lambda 1t, e to the lambda 2t, times b inverse. Okay, well, b is 2, 1, 1, minus 3, e to the 5t, 0, 0, e to the minus 2t, b inverse, which I'll write out in a second, but the point is I want to do this computation. When we run that, what do we get? We'll get 2 e to the 5t, e to the minus 2t, then we'll get e to the 5t, and we'll get minus 3 e to the minus 2t. And b inverse is minus 1/7, minus 3, minus 1, minus 1, 2. All right, last few comments. We gave this a different name previously. Do you remember what this was? Yeah, this was our phi of t that we talked about on the previous problem. And this was our phi of 0 inverse, which is to say that when we go back way back here, we have our phi of t, phi 0 inverse. It really does justify that this phi of t, phi 0 inverse is like e to the at. It's really working like that. All right, we'll pick up again next time with more examples. Thank you and have a good day.